So welcome to this section of our notes videos. We're going to start today with carbohydrates, or as Chemeter knows them, carbs. Okay.
I eat so many of them, they let me call them by their nickname.
Wow. All right. So we talked about in our first kind of introduction that we're looking at organic molecules, meaning they have carbon. So you'll see down here we have C to represent carbon. And carbohydrates specifically have one O, or oxygen, and two H, or hydrogen, for every carbon atom that they have. So you'll notice that that suspiciously looks like a water molecule, right? We said that water has two hydrogens and one oxygen. So we call carbs kind of hydrated. They have water, basically, because we have kind of this chemical makeup of two hydrogens and one oxygen for every carbon. Carbs are basically sugars, so anytime you're talking about any sorts of sugars, like in your foods that you're eating or anything along there, and they're polymers. So if you want to think about on this one, the sorts of foods that we're thinking of those starchy foods, so like bread and pasta and cereals, and anything that's got a lot of sugar in it. Mr. Hamele is showing you something now.
So that's the sugar, the monomer, basically, and the starchy stuff is the polymer. The long chain. Oh, Mr. Chemeter's bringing out competing toys. All right, who's got the best toys, guys? That's going to be one of the questions here in just a minute. So
there it is.
Ripley loses.
I tried.
All right. We were also talking about monomer-polymer relationships, and here is our first example of how that relationship plays out in this specific class of organic molecules, the sugars. So instead of just saying monomer, which is a general term for any monomer, we're going to talk more specifically about monomers for carbohydrates, which are sugars, and we're going to call them monosaccharides. And saccharides, another way of saying sugary, sweet goodness. I think that's the literal translation from, is that Latin? That must be Latin.
Can confirm.
Yeah, so monosaccharides are individual sugar building blocks. The biggest one that we're going to be talking about in this unit, and it's going to pop up again and again and again and again in future units, is glucose. Glucose is a hugely important molecule for your cells, my cells, and pretty much all the rest of the cells on planet Earth. So glucose is an example of a monomer, a building block for polysaccharides, which would be multiple monosaccharides put together. So we've got, again, that polymer-monomer relationship. But yeah, glucose, you're going to need to know its chemical formula, its structure. In fact, I think I should note why it's so important. I said it's important, but why is it important? It's the basic fuel, the energy source, raw energy source for your cells, my cells, plant cells, bacteria cells. It's energy storage galore. So it's kind of like, I don't know, what would what's the energy equivalent? I suppose traditionally it would be like coal and oil, but now we're transitioning hopefully to more fossil fuel, or not fossil fuels, more green energy. So we'll have to update our example later on. Okay, so like I was saying, knowing that molecular formula and the structure for glucose, Hamele is taking you on a circuit around the ring structure of glucose. We have the 5 carbons in the ring, and then 1 carbon up on a little stalk dangling off the top there. And we're not going to ask you to draw this from memory or anything like that. You know, maybe I shouldn't speak for the other bio teachers here, but I want you to recognize it. So if you were given a picture of a glucose molecule, you could say, oh, that's glucose. The way to recognize it is by that ring structure. I think that's the most characteristic part about it. You could also note too. Oh, go for it.
Oh, I was going to say, note that you've got 1 oxygen and 2 hydrogens.
You stole it from me. I was too slow.
I thought you were going to skip it, Chemeter.
I was like, too slow. Okay.
But so there's the hydrated carbon for you right there. And just another picture of it, just different model types.
Yep. But in all of them, you see the ring structure, and then you go, oh, glucose.
You have to make that noise every single time too.
Oh, glucose.
I can't match that tone. Yeah. So a disaccharide, so a monosaccharide is 1 saccharide, sugar. So what do you think a disaccharide is, Ripley?
It's a disappearing saccharide. It just disappears into nothingness.
Good try, but you're going to force me to go to Chemeter, which I don't want to do. What's a disaccharide, Chemeter?
It's a sugar molecule that you roll when you're playing Yahtzee.
You guys suck. All right. So, a disaccharide is two saccharides, two sugars, like glucose, stuck together to make a chain of two. So it's technically a polymer, but it's a disaccharide. And this is what we think of. When we think of sugar, we're really thinking of disaccharides. A monosaccharide is not sweet. Our tongues don't pick it up as sweet. It may be a sugar technically, but it doesn't bond up with our taste buds in a way that makes us think sweet. We need it to be a disaccharide, like fructose or sucrose that we have in fruits and things of that nature. So you can see here, there's one glucose and another one stuck together, a disaccharide. This is made in plants, generally. And we break it down into glucose for our own use. So we take this disaccharide in our digestive system, we'll snap it apart, get two monosaccharides that can then get into our bloodstream. They're now small enough to get into our blood, travel through our bloodstream, and get into our tissues, our muscles, and then we can use those for energy. Okay, so that is a disaccharide. Quick energy, because you only have to break it down in half in order to get it into your bloodstream, as opposed to what we're going to talk about next. It's going to take a lot longer to break down, so it's going to take longer to get in your system.
Which are our polysaccharides. Remember we said mono was just the one sugar, di was two, and poly means many, so we have many more sugars all bound together. As you can see, Mr. Hamele's got this long chain of them. And again, since they're so, it's going to take so much longer to break down, they're more typically long-term storage. So not kind of quick energy that you can use very fast. And we'll have some different names kind of in plants versus animals. So in plants, we call this starch, and we have, say plants are storing things long-term in starch molecules. In animals, we call it glycogen. And we found it often in muscles.
That is a cool shot, Kemeter.
Yeah.
So they were watching Star Trek and the Enterprise.
Very artsy. So we have starch and we have glycogen in animals. So that's what we have as our long-term kind of carb storage. And basically, again, just like we're seeing with our chain and Mr. Kemeter's lovely zooming by kind of chain of molecules, we have a bunch of little monomers, monosaccharides in this just long chain. And so that's going to be, again, your starchy foods, or where you're going to get these polysaccharides. So again, like breads, cereals, pastas, things like that.
Mm-hmm.
So it is. Yep.
Go ahead, Kemeter.
Nope, you're going to say what I'm going to say anyway, so you might as well say it. Nope. Well, I was going to say we've got just that reminder, the monosaccharide, and if this is glucose, if this is representing glucose, this is the raw energy source for your cells. So basically, you could kind of imagine your cells break this down, burn it for energy. And then when you've got extra of these things, like I ate a bunch of ice cream and cookies this weekend, I had extra glucose floating around in my body. So my body's like, hey, I'm going to store this stuff in case I need the energy later. And so it linked it together to form a polysaccharide, a big chain, that glycogen. And in between meals, when I'm not eating and my cells still need the energy, they can break off a piece of glucose and then use it for energy. Break off another piece of glucose, use it for energy. Break off glucose, use it for energy. And then maybe I eat again later because I have a tendency to do that. And I've got extra again, so I can build them back on. So this is a really great way to store energy and then use it, and then store it and use it. It's basically how the battery of your phone gets charged, and you use it, and then you have to charge it up again.
And some of you guys who are athletes may be using this to your advantage before an event or a meet. If you do anything called carbo loading, a lot of times you guys will get together like the night before and have a big pasta dinner or big pancake breakfast that morning. What you're doing is you're taking in all this starch. Your body is overloaded with it. It's breaking it down into sugars, gets into your bloodstream, spikes your blood sugar. Your body freaks out and says, no, that's too much. So it puts it back into that glycogen. Okay. And so you got a lot of this stored up in your muscles and your liver. Problem with glycogen in the human body, and like all carbohydrates, they can break down pretty easily in water, right? If you put a lollipop on your tongue, it's just going to dissolve, right? So this only lasts for about 24 hours. Okay, so the trick with carbo loading is you don't want to carbo load 2 days ahead of time, because then you're just going to have so much of this, your body will turn it into fat if you have too much of it, right? So if you eat it within 24 hours, it'll still be in this form. You'll still be able to, you're running your cross-country meet, you burn through all the sugar that's floating around your blood. Okay. Then your body says, okay, now we're going to start breaking apart this glycogen, getting sugar, and it'll keep you fueling. And when you're onto that, then you start burning fat. But that's kind of what carbo loading is all about, why you do a big starchy meal somewhere between 18 to 24 hours before your meet. It'll help get you that little bit extra energy to get through the meat. And there's just a picture of it. Just going to wait and see if anybody sees the joke here.
Is it the name of the car, the Cube?
The car is the Cube, but then look at the license plate for me. Do you recognize anything there, Mr. Kemeter?
Tennessee?
The license plate is the formula for glucose. Every glucose molecule, and we haven't mentioned this before, has 6 carbons, so C6. That means 6 carbons. Hydrogens, it has 12. And oxygens, it has 6. C6H12O6. That is the formula for glucose. You should know that formula. It's going to come up a lot.
It's a test question too.
Yep.
Because it comes up a lot. It's not just trivia. I mean, it's cool to know. I mean, if you want to know if someone's cool or not, just kind of like shuffle up alongside of them and go like, hey, do you know what C6H12O6 is? And if they look at you funny, then they don't know. They're not cool. But it's not trivial that we want you to know that, because later on, when we're talking about cell energy, it becomes important when we're starting to kind of do some molecular accounting in balancing formulas. So C6H12O6. Is this me again already? Or no, this is you.
This is Ripley.
This is Ripley?
What? I didn't sign up for this one.
No, Kemeter's closing. That's right. You're closing, Kemeter. This is you.
Me? Yes.
Oh, I thought you said it was Ripley.
No, it's yours.
If she opens, you close.
Okay. So not only are carbohydrates used for energy and some energy storage, depending on the way that you link them together. That's something we haven't mentioned yet. That's the difference between like starch and glycogen and other polysaccharides, is the order in which you link the molecules, the monomers together. So I could have a structure that's just a straight chain like this. I could also make one that is branching. So this could branch off to the side here. And now I've got, there we go, a bunch of craziness going on here. And that alters the properties of that polysaccharide. So again, if you think about the Legos, how you put the Legos together, even though they're the same pieces, how you physically connect them changes what you make. So here's an example of arrangements of monomers that produce structural components, really, really tough polymers that are rigid and able to do things like provide support, shape, and protection for plant cells. In fact, if you look around here I've got this meter stick is made out of wood, which is basically the leftover cell walls of plants. That's a polysaccharide that's made out of sugar. You can look at it. It doesn't taste like sugar anymore, but it's still made out of that glucose. It's just linked together differently. Same thing with insects. Their exoskeletons, the part that crunches when you step on them, that's made out of another polysaccharide called chitin. And again, because of how the monosaccharides, the monomers are linked together, it's a very tough, rigid structure. So it's cool. It's not just energy, but there's some structural components to cells that are based on carbohydrates too. Was that a good closing?
It was, other than the fact that you asked if it was a good closing.
Okay.
And with confidence. And that finishes our notes for carbohydrates.
Hold on. Let me try that again. Okay. That was a good closing.
Sure.
Okay.
That's it for carbohydrates. Join us next time as we delve into the wonderful world of lipids.
Anyone else hungry?
Oh, yeah. Let's go get something.